Take a directed graph G. We call G unilaterally connected or poorly connected if, for any pair of vertices U and V, G contains at most one of the paths U to V or V to U. Provide an algorithm to determine if a graph G meets this criteria of being unilaterally connected. So first, let's use some notation. Let's call the vertex set of GV and the edge set of GE. Now let's try and understand the problem. So I have an example here. This is an example of a poorly connected graph. How do we verify it's a poorly connected graph? Well, we just take every pair of vertices and check to make sure the condition is true. So let's take A and B. We see there is a path from A to B, but there is no path from B to A. So only one path exists and we're fine. We take A and C. We notice there is a path from A to C, but no path from C to A. Only one of the paths exists and we're fine. We take B and C. We notice there is a path from B to C, but no path from C to B. Only one of the paths exists and we're fine. Notice it's okay also for us to choose two vertices that have no paths between them at all. So we can take A and D. There's no path from A to D and no path from D to A, which is okay. It's okay for there to be no paths between two vertices. It's still considered poorly connected. Notice, however, though, if I add this edge, then if I take the vertices A to C, there is a path from A to C, but there is also a path from C to A. And therefore, this graph is no longer poorly connected. Okay, now let's try and solve the problem. The key insight in the problem lies with the fact that if you take any two vertices U and V, there is only the path from U to V or the path from V to U. There cannot be both. What that means is that U and V are not in the same strongly connected component. If they were in the same strongly connected component, then there would be a path from U to V and a path from V to U, by the definition of a strongly connected component. We know that's not the case. There's only one of the paths, and so U and V can't be in the same strongly connected component. There's also the possibility that there are no paths between U and V at all. There's no U to V path or V to U path. In that case, U and V are trivially not in the same strongly connected component because there's no path between them at all. So they can't be strongly connected. So suppose then we have 5 vertices. 1, 2, 3, 4, 5. No two of these vertices can be in the same strongly connected component. What does that mean? Well, they must all be in their own strongly connected component. Because no two of them can be in the same strongly connected component. They must be each in their own strongly connected component. And so there are going to be, in a poorly connected graph, V strongly connected components, where V is the number of vertices, like we talked about above. And so our algorithm has to check if, given a graph, the graph has V strongly connected components. Because if it has V strongly connected components, no two vertices are in the same strongly connected component, and the graph is poorly connected. So how do we check if there are V strongly connected components? Well, first we have to find the strongly connected components. So we can use Taryans or Kosarajus for that. And the output of Taryans or Kosarajus is the GSCC, or the graph of strongly connected components, which, as you recall, must be a DAG, or a directly acyclic graph, a directed acyclic graph. So, after we have the graph of strongly connected components, we have to check since each vertex in that graph of strongly connected components corresponds to a strongly connected component, we have to check if there are V vertices in the graph of strongly connected components. How do we do that? We can run BFS or DFS with a counter for vertices. It just keeps track of how many vertices we've encountered. If there are V vertices in the graph of strongly connected components, that means there are V strongly connected components, which means the graph is poorly connected. Otherwise, if there are not V strongly connected components, there are not V vertices in the graph of strongly connected components, the graph is not poorly connected. Okay. So we can analyze the runtime of this algorithm. We see that Taryons or Kosarajus will run in O of V plus E time. We also run a BFS or DFS on the graph of strongly connected components, which worst case has V vertices. So we're also going to have O, V plus E time there. Again, worst case, when there are V vertices, the graph of strongly connected components is the same as G. They're the same graph. And then all other operations are constant time, and so the total runtime of the algorithm is O of V plus E. Okay, I'm not going to go too much into the proof of correctness here, but we could do it with a contradiction. We could suppose any two vertices were in the same strongly connected component. If they were, then there would be a path, call them U and V, there would be a path from U to V and V to U, which means that this graph is not poorly connected. So you can follow it from there. You can also assume the proof of correctness of DFS or BFS and Taryons or Kosarajus. I also wanted to demonstrate this algorithm using the example we had above. So we have A, B, and C. When we run Taryons or Kosarajus on this graph, we will get the same graph because none of them are in the same connected component. Then we run DFS or BFS on this graph of strongly connected components. We see there are, with the counter, we run BFS or DFS with the counter, we see there are 3 vertices in the graph of strongly connected components. So thus, there are 3 strongly connected components. And since V is 3, we have V strongly connected components and the graph is poorly connected. If, however, there was an edge here, I'll draw it in red, then we see this entire graph would be 1 strongly connected component. And so the graph of strongly connected components would have 1 vertex when we run BFS or DFS, and 1 is not V, and so we would return that this graph is not poorly connected, which is correct. Also, an alternative solution for this involves seeing that G and also equivalently GSCC must be a DAG, and so we can simply check if G is a DAG by running DFS on it and checking for back edges.